Our third lesson, statistics, deals with how to graph quantitative data. So we're going to be looking at dot plots, stem and leaf, and line graphs. When you create a dot plot, that's the simplest way that you can display quantitative data. Basically, you take a small set of measurements, you put the measurements as points on a horizontal axis. Every time that the measurement occurs, you put a dot. If there's another measurement at the same spot, you put another dot on top of it. So the axis tells you whatever you're measuring, and then how many dots high it is tell you how many times that measurement occurred. We're going to look at these two example dot plots to create. Usually in class, I tell students to try them on their own, see what they would look like. So I'm going to show you how to do these two sample sets, then give you one to try, but it's absolutely fine if you just watch the video and follow along. So the first set, I'm trying to plot the points 2, 3, 6, 6, 7, 9. Here's the 2, here's the 3. Since 6 happens twice, we put them over top of each other. There's the 7 and there's the 9. When I make my axis, I just make sure it has to include the lowest and largest measurement. It does to a 9, so there's no reason I have to include 0 and 1 or go to 10 or anything. As long as it includes the extremes, I'm fine there. Going back a slide, this was the large set, so you can see everything's between 0.96 and 1.46. If we see how that's graphed, they started and showed 0.98 up to 1.47, so this would be the one representing 0.96, and that one over there represents 1.46. If I'm trying to see where things happen the most, it seems like it happens in this region here, is where I have a cluster of points. So the highest stack, I believe, is occurring at 1.10 there. But again, really the skill we're asking you to figure out here is just, I take the axis, I put a dot every time something occurs. Stem and leaf plots are a little weird at first. Honestly, I never learned them when I was in school. First time I encountered them was when I was teaching geometry. But after you get over kind of the layout of them and what they're trying to say, it's really not that bad to pull out points. So basically, these stems, these numbers that are to the left of this line, represent the tens digit. These numbers afterwards represent the singles digit. But each time one of these occurs, a new data point is occurring. So this has tens digit 1, singles digit 2. In other words, it's the data point 12. So it refers to that data point 12. Here, it's tens digit 1, singles digit 4, or 14, which refers to that data point 14. So this is 15, 15, and 17. Notice that I write 5 twice if 15 occurs twice in the data set. When I'm reading across this line, this is 21, 22, 27, 28. This is 30, 32, 38. So basically, you just need to see it as stems are the tens that go along with all the leaves that go after it. Each leaf represents a new data point. So somewhere you'd want to include a key that says this is tens and singles digits. That's kind of what's assumed, but there's a lot of times where maybe you'd want to use other digits. So for instance, there was a chart of millionaires where you were trying to say what's the average salary of a CEO from this and make a stem and leaf prop to describe the data. If I gave a problem like that, the CEO salaries, the stems would be tens of millions and the leaves would be in millions. So as long as I put a key that says 3 line 0 instead of representing 30, it would represent 30 million. So I'd write somewhere next to it 3 line 0 represents 30 million. As long as you do it for one data point and show what it is, that's an effective key that'll let somebody read the remainder of your graph. So you create a list of prices for different wireless routers you're considering using in your home to get internet. You find 15 popular brands with the following prices, $39, $45, so on. Create a stem and leaf plot from this data. So, a couple things I'd say here. First off, feel free to pause the video, try this on your own. If we were doing this in actual class, I would give you 5 minutes to attempt this on your own and try and create it yourself. And then when you see the next slide, I can go over things that might be common problems students have. Another thing I might suggest is when you get a data set like this, you might want to get used to putting them in order. It's fine if you're just trying to pull out and you say, oh, well, here I see a 29, that looks like the smallest number, it's the only 2, so I'm done with the 2s. Now I see a 39, 33, 39, I'm done with the 3s. Kind of cross off as you go, but in general, putting them in exact order is going to help us for stuff that we do later on with data sets. So getting used to rewriting a data set like this in order isn't the worst skill. Again, feel free to pause. I'm going to click ahead and show what my stem and leaf would look like. So this represents 29, 33, 39, 39, 45, 49, 51, 55, 60, 60, 66, 75, 79. This I want to point out. There's no leaves in the 8 row. That means none of the routers I was looking at cost $80-something. Because there's no leaves, we know there's no data points. That said, you don't want to skip a tens digit if there's other digits below it. So it's okay to have a gap in your graph where there is an unused stem with no leaves. It's not okay to skip a stem and, for instance, have gone from 7 right to 9. Here in the key, it says stems are $10 increments, leaves are $single, so it's fine to write it out, it's fine to show an example, but you want something that tells everybody what they're looking at in this stem and leaf. Last type of graph we're going to talk about for quantitative data is creating a line graph. So basically you want to make sure your data has time as the x-axis. A line graph is always measuring some quantity on the y-axis as it compares to time. When we talk about as it compares to time can be measured a lot of ways. It might be a science experiment where you're measuring the heat of something after every second. It might be a different experiment where you're in geological time and you're trying to say how much has this volcanic area changed over every 1,000 years. So even though it always has to be time, you can delineate time any way that you want. It can be in seconds, it can be in 10,000 years, it can be however best represents the data that you're trying to show. You want to choose a proper scale for the y-axis, make sure your minimum and maximum value are covered. There could be times where you want to compress the axis, so there's some debate over that, whether that's misleading or not. For me, if it's something where I'm measuring temperatures over the summer and every temperature is between 80 and 100 in the time that I'm looking at it, I don't know that I necessarily want to include 0 to 80 just as blank space on the graph. I might want to say that we're going to start at 70, for instance, so I can really see the changes that are happening. You're going to plot individual points of data corresponding to each date, so you're going to write them as a dot on your graph. Then you're going to connect those dots with straight lines. Part of the information that's being displayed is the slope between 2 points, so you want to make sure that these are straight lines drawn as you go along. As I've said before with graphs, you're always going to have Excel or some other computer program do that these days, so normally I'd say get out a ruler and connect your points, but really this is all just kind of telling you here's how you would make a graph, but in reality do it in Excel. Alright, so let's say we want to record the temperature Fahrenheit over the first 2 weeks of the fall semester as indicated in the following table. So as you can see, this is a table I made up in 2018. These are not real temperatures, I just made them up, but let's pretend they were real. We're trying to create a graph that shows from 9/1/2018 to 9/14/2018. Here's what the daily temperatures were. Again, feel free to pause the video if you like in order to try it on your own and then compare it to what I get, but I'm going to click ahead and show you how the line graph would look. So here, I do have 0 to 80 all shown. Again, it would be okay to write like 2 little lines saying that you're compressing this axis. As far as I'm concerned, it could start at 60 or 70 and still show the information. Really, you'd be able to see those differences better, but there is some dispute over whether that then distorts what you're trying to show. Regardless, here you can see that we start with this first point, which is the 1st of September. Then we go to here the 2nd, 3rd, so on, and each of these points is connected with a straight line. What this shows us is kind of the change in temperature over time. You can kind of see it almost has a sine curve to it where it went up and down and up again, but essentially what this allows us to see is how some quantity is changing over time. Last thing we're going to talk about here is just understanding the general shape of graphs. You're going to have to deal with some histograms in the next unit, which are a type of quantitative display, but we're really going to focus on them and frequency tables used to make them in the next lecture. So those will have some of these shapes that you might be asked which of these shapes apply to the graph. So the 4 key shapes that I want you to be able to identify. The first one is called uniform. So in a uniform distribution, every bar is the exact same height, meaning everything's equally likely to happen. So if you asked 10 people what their favorite color is, and 2 of them said red, 2 of them said blue, 2 of them said yellow, 2 of them said green, and 2 of them said orange. You'd have 5 colors, each of them had 2 people say it. That would be a uniform distribution, where each of the colors chosen was chosen the exact same number of times. Next type of graph we're looking at is a symmetric graph. So a symmetric graph is highest in the middle and then gets lower on the 2 sides at kind of an equal rate. So it slopes down here, where if you put a mirror in the middle, the 2 sides look about the same. That's called a bell curve. The entire 3rd and 4th unit in this class are based on that curve. It's extremely important in statistics, but all I need you to know at this point is if things have a general highest in the middle, then lower on either side distribution, that is called a symmetrical distribution. Also, again, could be called the could be called the bell curve or the normal distribution. And then in the middle here, you see that's listed mean, median, and mode. Those are terms we're going to learn later in this unit, but basically that's saying that all of them are happening in the middle when you have this shape. Second type, skewed left. Whenever I introduce skewed left and skewed right, I tell students right away it's the opposite of what you want it to be. The skew is the direction of the longer tail. So this graph, where things are piled up on the right and there's more data higher on the right, is skewed to the left because it has a longer left tail. So it's the opposite of what you want. Piled up on the right, skewed left. Piled up on the left, skewed right. General idea is skew pulls the mean in the direction of the skew. So basically, if I have this type of graph might be the grades on the first test. So I have a ton of students who are here getting A's, B's, but then some of the lower scores, let's say that the student gets a 10 on the exam, that's going to pull the mean down because I might have a few extreme scores on the low side that are far away from where everything's piled up. So even though a majority of the class is getting A's and B's, it might say that the average grade on the test is a 72. And that's because it has this type of distribution where the lower scores are pulling the distribution to the left. Other way that things could skew down here is a right skew. A right skew is when things are piled up on the left. So here, longer right tail pulls the mean out to the right. An example of a distribution that would be like this. If you had something that in a small business showed all the different salaries everybody was making in a small business. Let's say somebody's running a food truck. You have 3 people who are the people who make the food, who sell it, who are in the truck every day, and then you have one owner who's bankrolling the whole operation. If you tried to chart their salaries, maybe you have 3 people making $30,000 a year and then the owner making $100,000. What that would do is that would pull the mean out here, where the mean amount that somebody was making from this food truck would look like it's $45,000, let's say. But in reality, it's one person making all the money that's pulling the mean out. An outlier is what skews something this direction and pulls the mean that way. What I want you to take from this page is if you see a bar graph or histogram in the future, be able to tell, does it have this kind of distribution? If so, label it uniform. Does it have this kind of distribution? If so, call it symmetrical or normal. Does it have this kind of distribution? If so, call it right skewed. Call it left skewed. Piled up on the right, left skewed. I'm just trying to get it, sorry. And then if it has this kind of distribution, call it right skewed, piled up on the left. Apologies for that. So, last slide. Tell me what the shapes are of these 2 graphs. I'll give you few seconds here to think about it on your own, and I'll tell you what I would have said. First distribution, piled up on the right, longer left tail. This is left skewed. Second distribution, looks like a mirror down the middle, highest in the middle, same on either side. This would be a symmetric distribution.